This is the plant speciation model. When you press setup, plants will appear on one edge of the screen. All these plants have two traits that they inherit: the time of year that they will flower and the amount of tolerance that they have for heavy metal in the soil. In this first run of the model, I've set it up so plant offspring will be identical to their parents by setting the mutation rate for both flowering time and for metal tolerance to 0. As I run the model, notice that the day monitor will steadily increase. It'll keep doing that until the plants flower. This will happen for about 10 days in the middle of the year. And then when it reaches the end of the year, the days will go back to 0 and the number of years will increase by 1. The next year, the plants that are offspring from the previous plants will flower at the same time of year because they've inherited that trait from their parents and will be identical to the previous generation. Notice that as all the plants flower at the same time of year, this graph has a bar that remains in the same location. Its height changes as the number of plants increases or decreases with births and deaths, but its location, the time of year that plants flower at, isn't changing. Also notice how each new year, the region the plants are growing in tends to steadily expand into more of the ecosystem. This happens because as the plants die and drop their seeds into the soil near them, they gradually increase the space that they take up in the ecosystem. Let's see what happens after many years. I'm going to speed the model up by changing the visualized time steps from days to years. The model runs much faster now. I'm going to switch it back to days. Now, after many hundreds of years, notice where there are more plants. More in the green or the blue section of the ecosystem? Obviously more in the green. Notice this also appears on the flower time graph as two separate bars, one for green and one for blue. This corresponds to how many flowers having that flower time grow in the green region and how many grow in the blue region of the ecosystem. In this model, there's different environmental conditions on the left side of the ecosystem where the soil looks green, and on the right side of the ecosystem where the soil looks blue. This simulates two different types of soil. The green soil is more typical soil like you'd find in your backyard, but blue soil represents contaminated soil. It contains bits of heavy metal, like mercury, that is slowly dissolved into the soil in that area. You can see that the initial population of plants in this model was set up to better survive in the normal soil, based on the results we see right now. The initial plants had little tolerance for metals and don't survive as well over in this blue contaminated soil. They have roots that don't do well at absorbing water when it's contaminated with metal. But if an offspring of one of these plants has a mutation in their genetic information to produce greater metal tolerance, then it will survive a little bit better in the contaminated soil. But that advantage comes with a trade-off. Though mutation for increased tolerance will lead to the creation of a substance inside the plant that allows it to survive better in the contaminated soil, that also slows down its overall growth rate. So plants with greater metal tolerance would grow slower in normal soil compared to plants that don't have the mutation. In order to help visualize metal tolerance, plants will begin to look bluer the more mutations that they have in them that give them more tolerance for metal. Right now, all the plants have no tolerance for metal because they all started with no tolerance for metal and they incurred no mutations for it. I can see that by changing the show labels as from none to metal tolerance. Notice the zeros next to every plant showing they have no metal tolerance. I can also change it to flowering time, showing that at 183 days through the year, the plants will flower. 10 days later, their flowers will stop blooming. The graph for the tolerances also shows that plants both in the green and blue region have the same value. It shows there's more plants growing in the normal soil, shown by the green bar, than in the blue soil. Now I'm going to change the show labels as to metal in the soil. Notice that the amount of metal in the soil is a different label. And it shows values from 0 up to 100. as well as some intermediate values in between the two regions. Those represent where there's some metal in the soil. It's not completely contaminated there. So you can change the time steps or the show labels in this model to speed things up, slow things down, or visualize different attributes, but your graphs will really help you figure out what's going on in each region. Right now, all the flowers are the same species in both regions, because right now they're all able to reproduce with each other. I know this also because this graph shows the percentage of plants in the green region that are flowering at the same time as the plants in the blue region. Right now that value is 100%. Because they can flower at the same time, they can potentially pollinate with each other. And because of that, they can still potentially produce offspring with each other. Will that same outcome emerge when both flower times and metal tolerance traits can mutate and the offspring produced by the population? Well, use this model to investigate that question.